Welcome! In this video, we'll tackle LeetCode problem number 1737, titled Change Minimum Characters to Satisfy One of Three Conditions. We'll explore the problem statement, break it down step by step, and work through an efficient solution. Let's dive in and get started. In this problem, you are given two strings, A and B, each consisting of lowercase English letters. You can perform certain operations on either string to achieve specific conditions. The operation allowed is to change any character in A or B to any other lowercase English letter. The goal is to minimize the number of operations needed to satisfy one of three conditions. The first condition is that every character in A must be strictly less than every character in B in lexicographical order. The second condition is the reverse: every character in B must be strictly less than every character in A. Lastly, the third condition is that both A and B must consist of only one distinct character. The task is to calculate the minimum number of operations required to meet any one of these three conditions, and the input strings can have a length of up to 10,000 characters each. The output of this problem is a single integer that represents the minimum number of operations needed to satisfy one of the three conditions. Let's explore an example to understand this better. Suppose the input strings are A equals ABA and B equals CAA. The output in this case would be 2. To satisfy the first condition, where every character in A is strictly less than every character in B, we can change the C in B to B and also change the A in B to B. This transforms B into BBB, making all characters in A strictly less than those in B. The total operations performed here are 2. Now let's consider another example with A equals DABAD and B equals CDA. In this case, the output is 3. To satisfy the third condition, where both strings consist of only one distinct character, we can modify both strings to become AAA. For A, we would need 4 operations to make all its characters A, and for B, we would need 2 operations. However, the optimal solution is to make the necessary changes such that only the minimum number of operations is performed. Here, the optimal solution involves 3 operations, ensuring the third condition is satisfied. The constraints for this problem are that the lengths of A and B are both between 1 and 10,000, and the strings consist only of lowercase English letters from A to Z. There are also some edge cases to consider. For instance, if A equals A and B equals Z, no operations are needed since the first condition is already satisfied. If A and B are identical, such as A equals ABC and B equals ABC, the minimum operations would involve reducing both strings to a single distinct character. Additionally, when the strings are at their maximum length, the solution must be efficient enough to handle these large inputs within the constraints. To tackle LeetCode problem number 1737, we need to address the challenge of minimizing the character changes required to satisfy one of three conditions. These conditions involve either ensuring every character in string A is strictly less than every character in string B, flipping the inequality to make every character in B strictly less than every character in A, or transforming both strings so that they become identical. One straightforward way to approach this is through brute force. For the first two conditions, we can evaluate every possible split point between characters from A to Z to determine the necessary changes. For the third condition, the goal is to calculate how many modifications are required to make both strings identical by converting all characters to one common letter. While this approach is intuitive and easy to implement, it involves iterating over all 26 letters for every potential split point, resulting in a time complexity of O(26*) n plus m per condition. This linear growth with the size of the input can become inefficient for larger strings, making it less suitable for scenarios where performance is critical. To improve on the brute force approach, we can use optimized prefix sums with frequency counts. First, we calculate the frequency of each letter in both strings A and B. This allows us to efficiently compute the necessary changes for each of the three conditions. For the first condition, where every character in A must be strictly less than those in B, we use prefix sums to determine how many characters in A are greater than or equal to a given split point and how many characters in B are less than that same split point. Similarly, for the second condition, where B must be strictly less than A, we reverse their roles and repeat the process. The third condition, where the strings must become identical, is simplified by finding the maximum frequency of any single character in the combined string A plus B. The total number of changes required is the combined length of both strings minus this maximum frequency. By leveraging prefix sums and frequency counts, this approach reduces the time complexity to O n plus m plus 26, making it far more efficient than brute force. While this method is slightly more complex to implement, it uses basic data structures and scales well for larger inputs. The optimized prefix sums approach was chosen as the best solution for this problem due to its balance of efficiency and clarity. With a time complexity of O n plus m plus 26, this method scales effectively even for the largest inputs, where the lengths of strings a and b can reach up to 10 to the power of 4. By utilizing frequency counts and prefix sums, we can process the constant alphabet size of 26 letters in a time and space-efficient manner. This approach is particularly structured, allowing us to handle all three conditions systematically without unnecessary repetition. A key insight here is that conditions 1 and 2 can be reduced to comparing letters across a split point, which is where prefix sums shine in optimizing the computation. For condition 3, the problem simplifies to maximizing the frequency of a single letter, which further streamlines the solution. While pre-computing frequency counts and prefix sums introduces a small constant overhead, this is negligible compared to the significant runtime savings for larger inputs. Overall, this strategy combines clarity, scalability, and performance, making it the most suitable choice for this problem. In this problem, we are tasked with determining the minimum number of character changes required to make two strings, A and B, satisfy one of three conditions. These conditions are, first, all characters in A must be strictly smaller than all characters in B, second, all characters in B must be strictly smaller than all characters in A, or third, the two strings must become identical. To solve this efficiently, we take advantage of the fact that the strings only contain lowercase English letters, which means there are only 26 possible characters to consider. By using frequency arrays to count how often each character appears, and by computing prefix sums to track cumulative counts, we can calculate the number of changes needed for each condition in a time-efficient manner. This approach ensures that we can solve the problem in O n plus m time, where n and m are the lengths of the input strings. To implement the solution, we rely on three key data structures. First, we use two frequency arrays, frequency underscore A and frequency underscore B, each of size 26, to store the counts of each character in A and B. Second, we compute prefix sums for these frequency arrays to enable quick calculations of cumulative counts. Finally, we use counters to keep track of the total number of characters in A and B. The algorithm begins by initializing the frequency arrays. We iterate through each string, updating the respective counts for each character. For example, if A is ABC and B is CDE, the frequency arrays would look like this: frequency underscore A equals 1, 1, 1, 0, 0, and frequency underscore B equals 0, 0, 1, 1, 1, 0, 0. Next, we calculate the changes required for the third condition, where both strings are transformed into the same string. For each character, we determine the number of changes needed to make all of A and B equal to that character. This is computed as the length of A minus the frequency of the character in A, plus the length of B minus the frequency of the character in B. We then track the minimum of these values. Once the frequency arrays are set up, we compute prefix sums for both frequency underscore A and frequency underscore B. The prefix sum at index I represents the cumulative count of all characters from the start of the array up to I. For example, if frequency underscore A is 1, 1, 1, 0, 0, the prefix sum prefix underscore A will be 1, 2, 3, 3, 3. Using these prefix sums, we calculate the changes needed for the first and second conditions. For the first condition, where max, A, must be strictly less than min, B, the required changes are computed as the total characters in A minus the cumulative count of characters in A less than the current character, plus the cumulative count of characters in B up to the current character. Similarly, for the second condition, where max, B, must be strictly less than min, A, the changes are calculated as the total characters in B minus the cumulative count of characters in B less than the current character, plus the cumulative count of characters in A up to the current character. By iterating through all possible characters, we track the minimum changes for both conditions. Finally, we return the minimum number of changes across all three conditions. This involves comparing the results from the calculations for conditions 1, 2, and 3. In terms of complexity, the solution is highly efficient. The time complexity is O n plus m plus 26, which simplifies to O n plus m, since iterating over the 26 possible characters is constant. This efficiency is achieved by leveraging frequency arrays and prefix sums, which allow us to perform cumulative calculations in linear time. The space complexity is 26, due to the storage of the frequency and prefix arrays. Additionally, the algorithm handles a range of edge cases, such as when the strings consist of a single character, when they contain entirely identical characters, or when their characters overlap. This ensures robust performance across different inputs. To understand the algorithm better, let's walk through an example. Suppose the input strings are A equals ABA and B equals CAA. First, we construct the frequency arrays, frequency underscore A equals 2, 1, 0, 0, and frequency underscore B equals 2, 0, 1, 0. Next, we compute the prefix sums, prefix underscore A equals 2, 3, 3, 3, and prefix underscore B equals 2, 2, 3, 3. For condition 3, where both strings are transformed into the same string, the minimum changes required are 3, aligning both strings to A. For condition 1, ensuring max, A, min, B, the minimum changes required are also 3. For condition 2, ensuring max, B, min, A, the minimum changes required are 2. Comparing these results, the overall minimum is 2. Thus, the output for this example is 2, as it represents the fewest changes needed to satisfy one of the three conditions. Here, we start by importing the counter class from the collections module to help us count the frequency of characters in the given strings A and B. Inside the solution class, the min_characters method is defined. First, we use counter to calculate the frequency of each character in both strings and store these counts in count_A and count_B. Next, we prepare two arrays, frequency_A and frequency_B, to track the cumulative frequency of characters for easier comparisons later. These arrays are initialized with zeros and have a size of 26 to represent each letter of the alphabet. We then iterate over all 26 letters, represented by their indices from 0 to 25. For each index, the cumulative frequency of the current character is updated by adding the frequency of the character at the previous index. This ensures that frequency_A, I, and frequency_B, I, represent the total count of characters up to the current letter in their respective strings. Finally, we initialize a variable res to infinity, which will store the minimum number of changes required to satisfy any of the three conditions. The first condition is then addressed, making all characters in string A strictly less than all characters in B. For this, we iterate over the first 25 letters, as we don't need to consider changes for Z. The number of changes required is calculated as the characters in A that are not strictly less than the current letter, plus the characters in B that are strictly less than or equal to this letter. We take the minimum of this value and the current value of res to keep track of the smallest number of changes needed so far. Now, we move on to the second condition, making all characters in string be strictly less than all characters in A. This is similar to the first condition but with the roles of A and B swapped. We once again iterate over the first 25 letters, calculating the number of changes needed for this condition. Specifically, this is the number of characters in B that are not strictly less than the current letter, plus the characters in A that are strictly less than or equal to this letter. As with the first condition, we update res to be the minimum of its current value and the changes calculated for this condition. Finally, the third condition is to make both strings identical. For this, we iterate over all 26 letters of the alphabet. For each letter, the total number of changes required is calculated as the characters in A that are not equal to this letter, plus the characters in B that are not equal to this letter. This ensures that both strings would be made up entirely of this letter. Again, we update res to be the minimum of its current value and the changes calculated for this condition. Once all three conditions have been evaluated, the method returns res, which holds the minimum number of changes required to satisfy any one of the three conditions. Here, we start by defining our solution class and the min_characters method. The goal of this method is to determine the minimum number of changes required to satisfy one of three conditions for two given strings, A and B. First, we initialize two frequency count arrays, count A and count B, each of size 26 to represent the 26 lowercase letters. These arrays will store the character frequencies for strings A and B. We populate these arrays by iterating over each character in A and B and incrementing the corresponding index based on the character's position in the alphabet. Next, we create cumulative frequency arrays, cumulative A and cumulative B, which help us calculate prefix sums for the frequency counts. The cumulative arrays are built iteratively. If the index is greater than 0, the current cumulative value is the sum of the previous value and the current count. This setup ensures that we can quickly determine the number of characters before or after a certain position in the alphabet, which is essential for evaluating the conditions. Now that we have our frequency and cumulative arrays, we initialize the variable res to store the minimum number of changes, setting it to integer.max_value as a starting point. We also calculate the lengths of strings A and B for convenience. The first condition checks if all characters in A can be made strictly less than all characters in B. To achieve this, we iterate up to the second to last letter in the alphabet, summing the changes needed to reduce characters in A beyond the current character and increase characters in B up to the current character. We update res with the minimum value found. The second condition is similar but reversed, making all characters in B strictly less than those in A. Again, we iterate up to y and calculate the required changes. Finally, the third condition ensures all characters in A and B are the same. For each letter, we calculate the cost of converting all other characters in both strings to the current letter. After evaluating all three conditions, we return the smallest value of res, which represents the minimum changes required. To solve this problem, we start by analyzing the given strings A equals ABA and B equals CAA. The first step is to count the frequency of each character in both strings. For A, we get count_A equals 2, B, 1, meaning there are 2 occurrences of A and 1 occurrence of B. Similarly, for B, we calculate count_B equals C1, 2, which shows 2 occurrences of A and 1 occurrence of C. Next, we calculate the cumulative frequencies for each string, which track the total number of characters that are lexicographically less than or equal to each letter. We initialize 2 arrays, frequency_A and frequency_B, both of size 26 and filled with zeros. Then, for each letter from A to Z, we add the frequency of the current letter to the cumulative total. After processing all letters, frequency_A becomes 2, 3, 3, 3, indicating that up to B, there are 3 characters in A. Similarly, frequency_B is 2, 2, 3, 3, which shows that up to C, there are 3 characters in B. Now, we evaluate the first condition, ensuring that all characters in A are lexicographically smaller than all characters in B. This means we need to find a split point I from A to Y, where everything before I is in A and everything from I onward is in B. For each I, the number of changes required is calculated as len, A, frequency_A, I, plus frequency_B, I, which represents making all characters in A less than I and all characters in B greater than or equal to I. For example, for I equals 0, corresponding to A, the changes are 3, 2 plus 2 equals 3. For I equals 1, corresponding to B, the changes are 3, 3 plus 2 equals 2. Repeating this for all possible split points, the minimum number of changes for condition 1 is found to be 2. Similarly, for condition 2, the goal is to ensure all characters in B are lexicographically smaller than all characters in A. Here, we reverse the roles of frequency_A and frequency_B. For example, for I equals 0, the changes are 3, 2 plus 2 equals 3, and for I equals 1, the changes are 3, 2 plus 3 equals 4. The minimum number of changes for condition 2 comes out to be 3. Finally, we evaluate condition 3, which is about making both strings A and B identical by converting all their characters to the same letter. For each letter from A to Z, we calculate the total changes needed as len, A, count_A, letter, plus len, B, count_B, letter. This formula subtracts the number of characters in each string that already match the target letter and adds the remaining characters that need to be converted. For example, to make both strings identical to A, the changes required are 3, 2 plus 3, 2 equals 2. For B, the changes are 3, 1 plus 3, 0 equals 5, and for C, the changes are 3, 0 plus 3, 1 equals 5. The minimum number of changes for condition 3 is therefore 2. After calculating the results for all 3 conditions, the final answer is the minimum of these values, min, 2, 3, 2, equals 2. In the second example, with A equals ABC and B equals XYZ, we follow the same steps. First, we count the character frequencies. For A, we have count underscore A equals 1, B, 1, C, 1, indicating one occurrence of each letter. For B, we get count underscore B equals X, 1, Y, 1, Z, 1. Next, we compute the cumulative frequencies. For frequency underscore A, the cumulative counts grow to 1, 2, 3, 3, reflecting the 3 characters in A. For frequency underscore B, the cumulative frequencies are 0, 0, 0, 3, with non-zero values starting at X. To evaluate condition 1, where all characters in A should be less than all characters in B, we calculate the required changes for each split point. For instance, at I equals 24, the changes are minimal at 3. For condition 2, with B being less than A, we reverse the roles of frequency underscore A and frequency underscore B. Again, the minimum number of changes is 3. For condition 3, we aim to make both strings identical by converting all characters to the same letter. Using the formula len, A, count underscore A, letter, plus len, B, count underscore B, letter, we calculate the changes required for each letter. Since A and B have no letters in common, the minimum number of changes is 6, as we must convert all characters in both strings. Comparing the results for the 3 conditions, we find that the minimum of 3, 3, and 6 is 3. Therefore, the final answer for this example is 3. To analyze the time complexity of our solution, we break it down into the key operations performed. First, counting the frequency of characters in both strings using the counter function takes O, N, for string A and O, M, for string B, where N and M are their respective lengths. Next, we construct cumulative frequency arrays for the 26 lowercase English letters. Since the alphabet size is fixed, iterating over these letters and updating cumulative sums takes O, 26, which simplifies to O, 1. Then, we evaluate the loops for the first 2 conditions. These loops iterate over the range of 25 alphabet indices, performing constant time calculations for each index. As a result, each loop contributes O, 25, which again simplifies to O, 1, due to the constant size of the alphabet. Now, for the third condition, which involves making all characters in both strings equal to a single letter, we loop over the 26 lowercase letters. Similar to the previous loops, this operation involves a constant amount of work for each letter, which results in O, 26, or O, 1, time complexity. Combining all these steps, the overall time complexity of the solution is dominated by the frequency counting step, which is O, N plus M. The other operations, such as constructing cumulative arrays and iterating over the fixed alphabet size, are constant time and do not depend on the input size. Therefore, the final time complexity of the algorithm is O, N plus M, where N and M represent the lengths of the input strings. Turning to the space complexity, we start with the frequency counters. The counter objects for strings A and B store the frequency of each lowercase letter, which requires O, 26, space per string. Since the alphabet size is constant, this simplifies to O, 1. Similarly, the cumulative frequency arrays frequency underscore A and frequency underscore B store 26 integers each, contributing another O, 26, or O, 1, to the space complexity. Additional variables such as res and the loop index I require only O, 1, space. In conclusion, the overall space complexity is determined by the frequency counters and cumulative arrays, both of which operate within the fixed alphabet size. This leads to a total space complexity of O, 1, as no extra memory is required that grows with the input size. When comparing this optimized solution to a brute force approach, the difference is significant. A naive solution would involve checking all possible character transformations for both strings to satisfy each condition. This would result in a time complexity of O, N asterisk M, for conditions 1 and 2, and O, N asterisk M, for condition 3. In contrast, our optimized solution reduces this to O, N plus M, by using frequency counts and cumulative arrays, making it much more efficient. Moreover, the time complexity remains O, N plus M, for all input cases best, average, and worst, since the algorithm processes the input in a single pass and operates within a constant alphabet size. The mathematical proof behind this complexity lies in the dominance of the O, N plus M, term from frequency counting, while all other operations remain constant time. The space complexity, on the other hand, is 1 due to the fixed alphabet size, ensuring that no additional memory usage scales with the input size. Common mistakes in this problem often stem from misunderstanding the three conditions that must be satisfied. It's crucial to remember that the conditions strict inequality, lexicographical order, and equality are independent, meaning you need to evaluate each one separately to find the minimum cost. Overlooking even one condition can lead to partial or incorrect solutions. Another frequent mistake is inefficiency in frequency calculations. Instead of pre-computing character frequencies, some solutions recompute them repeatedly during comparisons. This unnecessarily increases the time complexity, which can be a significant issue for larger inputs. Finally, ignoring edge cases is a common pitfall. For example, consider strings where all characters are the same, strings of length 1, or scenarios where one string needs a complete transformation. Overlooking these cases can cause your solution to break during testing or interviews. Many errors also arise from improper handling of lexicographical constraints. Conditions 1 and 2 require you to evaluate all possible split points from A to Z, and missing even one can lead to an incorrect result. Each split represents a potential boundary for lexicographical ordering, so it's essential to check them systematically. Another significant issue is failing to optimize character comparisons. Brute force approaches that compare all characters individually can become computationally expensive. Instead, leveraging cumulative frequency arrays allows for efficient prefix and suffix calculations, significantly reducing computation time. Neglecting these optimizations increases the likelihood that your solution will exceed time limits when tested on larger strings. To excel in interviews, there are several key insights to keep in mind. First, pre-computing frequency arrays for both strings is a foundational step for optimizing prefix and suffix calculations. This not only simplifies comparisons but also ensures your solution is efficient. Second, remember that conditions 1 and 2 deal with lexicographical ordering, such as ensuring all characters in one string are less than those in the other. By using cumulative frequency sums, you can quickly determine the number of changes required for each potential split point. Third, for condition 3, which focuses on equality, the optimal strategy is to identify the most frequent character in the combined strings. This minimizes the number of changes needed to make both strings uniform. Finally, always test your solution against edge cases, such as strings with a single character, completely disjoint character sets, or scenarios with overlapping characters. These tests ensure robustness and reliability. Additionally, exploring related problems like LeetCode 1832 or 1163 can help strengthen your understanding of similar challenges. There are also alternative approaches worth noting. A brute force method involves comparing all possible transformations of the strings to satisfy each condition. While this approach is straightforward and can help with understanding problem fundamentals, it's computationally inefficient with a time complexity of n squared. A more practical strategy is optimized frequency calculation. By using cumulative frequency arrays, you can compute changes for conditions 1 and 2 and 26 for each character, reducing the overall complexity to n plus 26 squared. This approach is slightly more complex to implement but offers significant performance gains. Another advanced option is dynamic programming, which can be used to track the minimum changes dynamically across conditions. While this method is uncommon and often overkill for this particular problem, it could prove useful for tackling similar lexicographical challenges in other contexts. These alternatives provide flexibility depending on the constraints and goals of your implementation. Great job making it through. Today, we reviewed an efficient approach to solve LeetCode problem number 1737 by leveraging frequency analysis and prefix sums. We hope you found the explanation clear and insightful. Remember to like, subscribe, and keep practicing those coding challenges. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!